So, today, yeah. Yes. Yesterday's mid segments were fairly straightforward. Today, we'll go back and look at it before we're done. Today we're going to talk about about perpendicular bisectors, but let's first get a good idea of what a perpendicular bisector is, because we're going to have a whole bunch of special segments that we're dealing with. So a perpendicular bisector, to start with, stop talking. To have a perpendicular bisector, we have to start with a segment. And in order to be a bisector, it has to go through what point on that segment? The midpoint. So we're going to go ahead and we're going to construct a point at the midpoint on the segment. Now, a bisector is another line or something like that that goes through the midpoint. So I need to tell it what to be perpendicular to, as well as where the midpoint is, and I can construct a perpendicular line. This line that we see now is the perpendicular bisector of that segment. It doesn't matter where I move the segment. It doesn't matter how long or short I make it. That point is always at the midpoint. That is always a right angle between the two. Okay? So we first need to start with a basic understanding of what a perpendicular bisector is. Now, I'm going to put another point. I'm going to put a point on the perpendicular bisector. And I'm going to go ahead and name that point. No, let's try naming the point A. All right, the other points here are B and C. And now I'm going to measure the distance from A to B. And from A to C. Oops. No, I don't want the whole line. I just want C. Guys. Stop. What do you notice about those two distances? They're the same. So A is equally distant from both B and C, isn't it? Does it matter where A is on my segment? No, it doesn't. Does it matter if my segment is a little shorter and maybe at an angle instead of straight up and down? Are the distances still the same? The distances keep changing, but the distances are always the same, aren't they? So I can say, based on observation here, this is not a proof. This is more of a inductive reasoning instead of deductive. But based on what I'm observing here, what would you say? A point on the perpendicular bisector is always, and we're going to use a big fancy word here, equidistant, of equal distance, equidistant from the endpoints of the segment that's being bisected. So a point A on the perpendicular bisector, that's that line, any point I pick is always equally distant from the two endpoints of the segment being bisected. Conversely, if I put another point out here, not on the perpendicular bisector, and then I measure the distance between those 2 points, all right, I'm going to move these measurements over here just so they're different, in between D and C. No, those are not the same, are they? When will they be the same? Are they the same now? No. Okay.
You just got it.
I want
there.
Oh, in order for them to be the same, where is the point going to have to be? Well, okay.
Yep.
It's going to be hard to get it precise with my fingertip, okay?
Do it. You can do it. There.
Oh, you can.
Jordan.
Oh, so close. Oh well, you can fix that. Display. This is Geometry Sketchpad. We used to have students do it all the time, but
why not anymore?
It just.
You just not trust us?
let's go ahead, distance to the tenth. Oh, it didn't switch those back. Okay. So, but anyway, what we're seeing is that in order for the distances to be the same, the point has to be on the perpendicular bisector. So again, it's just kind of reinforcing that whole thing. Why is that true? Well, let's think about this for a second. We know this is a midpoint, right? We know this is a midpoint, so this is congruent to this. We know this is perpendicular, so that's a right angle. And no matter where this point is, we have a reflexive property for that side. So if I make that triangle, why are those two triangles congruent? What theorem? Side angle side. It's not HL. It is a right angle, but it's not HL in this case because it's not the hypotenuses. It's side angle side. So that's kind of why, but the fact of the matter is we don't have those lines necessarily drawn in. So it's just a little bit different in how we look at things. But that's the idea with perpendicular bisectors. And the proof uses side angle side. We kind of use more inductive reasoning. And so that's kind of where the sketch pad is here, or the notebook. We can conclude that AC and DC and AC here, similar picture, that DC has to be congruent to AC. Even though they're not drawn in, they still exist. We can conclude they're congruent. In a triangle, each side has its own perpendicular bisector, because we're working with triangles, not just segments here, right? We'll work a little bit with just segments, but in a triangle, all three sides will have perpendicular bisectors, and that's drawn in here. And I could go back to my sketch pad and do that. We could go ahead and make ourselves, whoops, nope, sorry, wrong button. Sketch pad. No, oh, sorry, wrong button. All right, here we go. I could make another segment here from here to here, and make another segment from here to here. And there it created a triangle. Now I'm going to create the perpendicular bisector of each side. So I have to put the midpoints on the side. We can construct midpoints on each side. And then I'm going to construct a perpendicular line here. And I'm going to construct a perpendicular line here. Notice all 3 points intersect at that common point of intersection, don't they? And it doesn't matter what kind of triangle we have. That line could be outside. That point of intersection might be outside the triangle. It might be inside the triangle. It might be actually on the triangle. But every time I create a triangle, the 3 lines, the 3 perpendicular bisectors, which I'm going to change the color so we can identify them. Let's make those red. Okay, the red lines are perpendicular bisectors. All 3 intersect at a common point, no matter where the triangle is. So that's kind of interesting, because you wouldn't necessarily expect that all 3 of them, I mean, obviously 2 of them will, but all 3 of them always come to the same point, no matter what kind of triangle I have. No matter how I manipulate this triangle, make it larger or smaller, like I said, sometimes that point of intersection is outside the triangle. Sometimes it's inside the triangle. But I know a perpendicular bisector is always equidistant from the end points of the segment being bisected. So that means that this point here is equidistant from these 2 endpoints here. Those 2 distances have to be congruent because I'm the perpendicular bisector of that segment. But it's also the perpendicular bisector of this segment, so these must be congruent. So this point that is created is equally distant from all 3 vertices of the triangle. Some would consider this the center of the triangle, because it is the distance from that point to a vertex, to each vertex, is exactly the same. And in fact, because of that, and here's where it gets really fun, I can actually construct a circle using that as my, whoops, first I gotta get rid of that. Using that as my center point, and this is my radius. Notice that circle fits perfectly through all 3 points of the triangle. Or we are saying we are circumscribing, which means to write around. Circum means around, scribe, to write. We are circumscribing a circle around the triangle. And again, it doesn't matter if the point of intersection is on the inside, on the outside, where? Point of intersection on the outside, we can still do it. Point of intersection on the circle, we still do it. It works no matter what. Okay? No matter how you manipulate that triangle, that circle still passes through all 3 points, which is why we call this point, we're going to label it here, not J. Stop that. No. I want to label the point. All right, now I'm going to rename that. No. Here we go. I can give that a name I want. We're going to name it, it's called the circumcenter. C-U-O, I spelled it wrong, didn't I? It's C-R-C-U-M. Sorry, typo. That's called the circumcenter of the circle. Sorry, circumcenter of the triangle. That's what it's called. So where the 3 perpendicular bisectors intersect is called the circumcenter. Now that's a lot to memorize. We've got a lot of things here in this section. Unlike yesterday where we just dealt with mid-segments, which are easy because they're parallel to a side and half the length of a side, this is more complicated. The circumcenter is the point of intersection of all 3 perpendicular bisectors. So first we have to know what perpendicular bisectors are, and then we have to know what a point of intersection is, and then the whole bit. And that's the way that circumcenters work, and they are equidistant from the vertices of the triangle. That's a lot to remember. So how can we help remember that? Okay, this is kind of walking through what I just did. It's in written form. If you're interested in the notes in written form, I will certainly post those online. They will not include all the sketchpad drawings we just did. The podcast will. It is equidistant from all 3 vertices, and it's helpful to see it drawn, not just, or constructed, not just drawn as a picture. And like I said, the circumcenter is not always inside the triangle. When the triangle is obtuse, the circumcenter may be outside the triangle, and that's fine. I'm still getting the point of intersection of all 3 perpendicular bisectors, and I'm still taking that distance dA to dB to dC. All 3 of those segments are congruent. Those are the congruent segments. And it even works when it's on the triangle. That's a right triangle, by the way. When it's on the triangle, this is going to be a right triangle. It's inside when the triangle's acute. It's outside when it is. So here's a quick summary of what's going on. Yesterday we learned about mid-segments. Mid-segments connect 2 midpoints. They're parallel to a side, and they have half the length of the side it's parallel to. Perpendicular bisectors go through a midpoint and are perpendicular to the side. Notice they do not pass through any vertex of the triangle in most cases. If I go back to my sketch, these 3 perpendicular bisectors are not passing through the vertices of the triangle, are they? Is it possible that they could in some circumstances? Oh yeah. All right, I mean I could manipulate it so there, it's going through a vertex. It's not going through a vertex here or there. I mean, it can, by chance, sometimes pass through, but not always. And that was what kind of by design, actually. Not by chance. They are perpendicular to the side. The point of concurrence is called the circumcenter. It is equidistant from the vertices of the triangle. So this is information that you'd want on flashcards. Okay? The front of, if this is the back of your flashcard, the front of your flashcard might be something like this. okay? And you mark in a midpoint and a line coming through like this with a right angle. On the back, you then know it's a perpendicular bisector. It goes through a midpoint. It is perpendicular to a side. The point of concurrence is called the circumcenter. That's what we call where all three lines intersect is called a point of concurrence. Okay, they're concurrent. They're the same place at the same time. That's what concurrent means. So that's what we're doing today. We're looking at circumcenters and stuff like that. Now, how does it play out in the homework? That's the question. Okay, so we've got these facts. What kind of problems do we ask as a result of these types of situations? Okay. First thing we do is let's take a look at what the assignment is going to be. There we go. So you might want to jot this down. It's 306, 1 through 17, and 20 through 22. Sorry, I'm turning into it myself. Some of it just deals with perpendicular bisectors, okay? So some of it just deals with, okay, here's a segment. All right. This is the perpendicular bisector. And A, B, C. And it might say something like AB equals 7, BC equals X plus 9. I'm sorry, yeah. And then you have to set up and solve an equation based on that. Well, if that point's in the perpendicular bisector, what must be true? What must be true if that point's in the perpendicular bisector? What would we say? A point on the perpendicular bisector is, what's that big word? Starts with an E.
Something.
Is anybody paying attention?
I just got it.
Equidistant.
I was going to say that.
Okay. It is equidistant from the endpoints, which means what has to be true about A, B, and B, C?
Congruent.
It has to be congruent, so 7 equals X plus 9. And that's, you know, no big deal. X is negative 2. That's fine. So you have questions of that level. Questions like that. You'll have other questions that deal with, okay, give you a triangle with all three perpendicular bisectors drawn in. Okay? So I've got this perpendicular bisector, and I've got this perpendicular bisector, and I've got this perpendicular bisector. Okay? What's that point called? Which center? It's the circumcenter. Okay? But then it'll have this drawn in. The three red segments here. And it'll say, okay, this segment equals 8. How long is this red segment here going to have to be?
17.
Yeah. The circumcenter is equidistant from the vertices, so we'll have to know that those are going to be the equal distances. Not the distance from here to here, not the distance from here to here. It's the distance to the vertex that is congruent. So you'll be using that. And yeah, that's pretty much what you're working with today. And honestly, these mid-segments and circumcenters are really the only two things that are on this next benchmark. so by tomorrow, we're reviewing already. And on Monday, we're taking our next benchmark.
What we doing Tuesday?
Oh, we start the next one. We start E2.
Good.
So, yeah. 20 through 22. Pretty straightforward. So that's what we got going today. Okay?